Okay, so in this graph, we'll compare between the agonist, antagonist, and the inverse agonist. So before we have any molecule bound to the receptor in the resting state, before we add any agonist, antagonist, or inverse, this is how it looks like. This is what the receptor will look like before the addition of any drug or any ligand. You will have, for example, if you have 5 receptors, you will have one of them in the active conformation and 4 of them in the inactive conformation. So basically you have 1 of 5, which is 20% of the receptors in the active form. Okay, so this is the active form and this is the inactive form. So this is before you add any agonist or antagonist or inverse agonist or even an endogenous ligand. And I should say that another way to think about it is that this receptor or any one of these receptors would be spending 20% of its time here and then the other 80% of their time here. Okay, this is to be consistent with how I described it in the class. Okay, and then in the first example, which is the example of the addition of an agonist, when you add an agonist like this, it's going to bind to the binding site here, and then it's going to shift the receptor from this form, inactive form, into the active form. In this case, you have out of the 4, we were able to shift 4 of them, 3 of them to the active form. So now we have 4 of the 5 receptors in the active form and 1 of them was still in the inactive form. And in this case you will have an increase in the activity. So instead of having the steady state where you have 1 of 5, now you have 4 out of 5 in the active form because of the binding of the agonist, or you can think of the endogenous ligand as an agonist which binds to the receptors and move them to the site. Now can I have all of them be moved to this active site? Of course you can. If you have a stronger agonist or a full agonist, then you could actually, by binding of the agonist to the receptor, you would see all the receptors coming to the site, to the active conformation, the active form of the receptor, and then reduce the biological activity. Now in the case of the antagonist, notice that the antagonist would bind to the receptor. Let's say it binds somewhere here and blocks the binding site for the agonist. So it would prevent the agonist from binding and activating these receptors and moving them to the active form. So it would actually maintain the resting state. See the antagonist here. In the case of the antagonist, it is exactly similar to the case of having the resting state where you have only one of the receptors in the active form and the others are inactive. And then of course if we try to add an endogenous ligand or an agonist, these antagonists are going to prevent the agonists or the endogenous ligands from binding them. They're gonna stop them from binding to their binding site, and then you will have again the same resting states. Now with the case of an inverse agonist, notice that the inverse agonist typically binds to a binding site that is totally different from those for the agonist and antagonist. In the case of the inverse, instead of having this one receptor in the resting state, instead of having one in the active form, you will even take this one away to become inactive. So you would withdraw the intrinsic activity of the receptor. So if we have 1 of 5 in the resting state as active, that's 20%. Here you have none of the 5 as active because of the inverse agonist. So the inverse agonist was able to bind to this receptor, change its conformation into the inactive form. So now I have all these 5 receptors in the inactive form. And so you would have 0 zero activity here, as compared to having 20% activity in the resting state. And then of course in the agonist we said 80%. In the antagonist we still had the 20%. We were not able to increase it. So hopefully this video will help you differentiate between the three kinds of agonist, antagonist, and inverse agonist. And you can imagine in the case of a partial agonist that maybe some of these would be activated and not all of them. So instead of having 4, we might have 2, and then the rest are here. That's in the case of the partial agonist.